I hope you've enjoyed your weeks here so far. Langley's a great place to work. I've worked here. I just hit 25 years service, so it's been a fun time. I started when I was an intern in college, and that's something I highly recommend to students if they want to get involved, not just in the sciences, but almost any field, is to try an internship in college. Not only is a way for them to make some money over the summer, but also to get a little bit of experience, find out if their chosen job area is something they really are interested in working. It's a great way to get your foot in the door, because if you impress that employer, you might get a job there afterwards. So you need all kinds of ways to get a foot in the door in this kind of economy. So I always recommend to students to try and look for internships. And actually some college curriculums, like the one I went through at the University of Louisville, actually they required an internship as part of the undergraduate program. So that really works out well. Today I'm going to give you a little bit of background on a couple of projects I've been involved in the last several years. Kind of a culmination of it's a combination of work in what we call photogrammetry, but also computer graphics and application of mathematics. And in particular, I'll show you how this has been applied to a couple of both a launch test and to some water drop tests. But first of all, I'll tell you a little bit about what I mean by photogrammetry. The principle is actually fairly simple. It's the idea of using either photographs or video to measure or understand an object in the real world. It might be as simple, for example, as a video of a car passing left to right in front of you. If you know something about the size of the car, you should be able to take measurements from the video to determine its position and its velocity. Photogrammetry is used quite a bit in crime scene investigation, even years after the crime may have occurred, if they have photographs still available, because they can actually take measurements off a photograph. Say if it's a car collision, from measurements on the photograph you can determine things like the velocity of the vehicle and the orientation of the vehicle, or one or more vehicles in that case. Was there a question online or something? So the photogrammetry has actually been around for 150 years at least, and even Leonardo da Vinci had some early ideas about photogrammetry because he had a lot of understanding of the projection of light rays onto a canvas, for example. In much the same way that light rays are projected into our eye or into a camera, it's all described by perspective geometry or projection geometry, and we'll see a little bit of that. My colleague on this experiment was Sam Miller. He also works here at Langley, and he just got back from some studies working on his PhD. Together he and I applied or developed some of these algorithms that you'll see to work with this launch test. So photogrammetry can use one or more cameras. In this case we used as many as 4 cameras simultaneously during the test. Langley has quite a few high-speed cameras that are used for quite a variety of tests out here. These high-speed video cameras are capable of going up to, I believe, 50,000 frames per second. That's fast enough to see a bullet pass by. You can run them as slow as 30 frames a second, standard video, but they can go up to quite a high speed. For our experiments, we went up to 1,000 frames per second. That was sufficient for our needs. The image on the left is an actual photograph from a launch of what was called the Max Launch Abort System, or MLAS for short. That was flown out of Wallops Island in Virginia a couple years ago. We'll look at that in more detail. And the image on the right, with the space capsule looking object about to hit the water, is from an experiment we did last year as well as this year, looking at splashdowns, similar to the old Apollo splashdowns. So let's look at an outline here. I'm going to give you an overview of that Max Launch Abort System, what it was about, where it was flown, and why we did it. We'll talk about the cameras that we had on board the Max Launch Abort System and how we use those cameras to measure the performance and what we call the degrees of freedom of the vehicle. We'll go into a little bit about how we used our cameras, how we calibrated them. Almost with any as you may know, any measurement you make with almost any device, you usually have to calibrate that device in order to get good measurements out of it. We'll look a little more in detail at the computer software or algorithm that we developed for the photogrammetry analysis, look at some results, and look at how we applied that to the water landing tests and other tests, and look at some possible future applications. By the way, we do have plenty of time, so if you have any questions, feel free to interrupt me as we go along. Has anyone heard of photogrammetry before, or have seen it in action? There's a couple of folks. It's widely used. It's actually been used for the past 150 years to use. It can be used in aerial photography if you have. You can take images separated by a mile or more and get some information about the topography of the mountains and the hills underneath the airplane. It's also used in surveying. It's used in engineering and data quality control. It's used quite a bit at the shipyard here in Newport News to scan in a very large hull of a ship to make sure there's no significant deformations in the hull. You can also supplement photogrammetry with active laser systems or LiDARs to measure deflections in surfaces. A question over there.
Sports applications like a tennis racket hitting a tennis ball and the tennis ball getting squished and the racket getting extended also?
I can think, as you'll see, it's important to put targets or known points, or mark them with some kind of reflective material, and the camera can track those objects and can track the motion of the athlete or the racket that they hold in their hand. It's used quite a bit in Hollywood too to match computer-generated imagery with the actors or live action, and you'll see an application of that we used here at NASA to combine computer-generated imagery with video from these cameras. I've also read that archaeologists can use photogrammetry quite a bit too, as they gather photographs of a excavation from multiple different angles. They can start to reconstruct what the original environment may have looked like eons ago. So it's quite a prolific use of photogrammetry for 100 years in many different applications, and you'll see how we use it today. As you might imagine, with the advent of and ease of digital photography in recent years, the use of photogrammetry has really exploded. So you don't have to wait any longer for film or worry about distortion that the film process may induce. All you have to worry about is the distortion that's in your camera. Then we'll show you how you can calibrate your cameras and quantify any noise or distortion. So let's look at this, the Max Launch Abort System flight test vehicle. It was a alternative concept as a way to, it's also called a launch escape system. The idea is to get the crew away from a large rocket in case the rocket has an emergency, the rocket explodes or something. If the crew is on top of the rocket, you get them away from the vehicle safely and quickly. The crew may experience quite a few G's in that process, getting away from the vehicle if the rocket's exploding, but the idea is they would survive and they would land safely on the Earth, getting away from the launch pad. Launch abort systems have been in use ever since the early Soviet launches and American launches. There was the Mercury and Apollo launches did use a launch abort system on the very top. Jettison motors were used to, in case of an emergency, to get the crew vehicle off of the rocket stack and out to safety. It was never used for Apollo or Mercury. It's only been used once, from what I've read, and that was used by the Soviets. They actually had an emergency occur in 1983. There was a launch pad explosion, and the Soviets, they did use their launch abort system, and it successfully did get the crew off the vehicle and over to safety. So it does happen, and these systems do work. The crew experienced about 15 G's in the process, and they were bruised up a bit, but they did survive, and that's the important thing, is to get the crew away from the rocket and survive. So NASA certainly intends to have a system like that on future rockets, and that's why we are researching them. So The Max Launch Abort system is an alternative concept that has not been used on an actual crewed vehicle. This launch was unmanned. There were no people on board. It was just a test to try out the concept. The idea is that you would have crew in the crew module. You can see on the lower right, you might be able to see people in the image to get a feel for the size of this crew module. And there's this forward fairing or canopy over the crew module to protect it during the launch. And then there's the boost skirt and motors underneath this to get it to its test altitude. In the upper right, you'll see just inside that canopy or the forward fairing are all these targets, all those bright spots or targets. Each one's about an inch in diameter. As you'll see, these targets are known locations or known markings on the object that our cameras can track so that we can deduce the motion and orientation of the vehicle over time. So this vehicle, the final vehicle stack was about 33 feet high. It's not on top of a rocket, it's just a test launch, but we did use rocket motors to get this up to a test altitude. The whole experiment lasted just a couple minutes, but it was a successful launch. It occurred in July of 2009. It was at Wallops Flight Facility on the shore of Virginia. This gives you a concept of all the sequence of operations in the flight. You have a power descent with the rockets underneath the crew vehicle, and the various components start to separate as you reach the top of this parabola. And then the parachutes start to deploy and slow down the vehicle. Remember, this is unmanned, but presumably in the future you would have crew inside that crew module. Where's my mouse? Here we go. So imagine that we have crew in this module. They've been through quite a few Gs, and now they're rotating around. But again, the idea is to get them to safety, get them away from a rocket that might be failing. And the parachutes come out, and eventually the crew module separates from that forward fairing or the canopy and falls to safety with the aid of these parachutes. We were particularly interested in this region here, the separation of the crew module from its forward fairing. And in fact, below there you see an actual sequence of photos of that separation sequence. You see this crew module coming out of the canopy that shrouds it. There was some worry that these two components might collide with each other as one is coming out. So this is where our cameras, our photogrammetry system, was focused on these two objects to make sure that we didn't have any collision between the two, and actually to understand how fast they separated and exactly how many degrees did it rotate in the process. So it happens quite quickly in just a fraction of a second, but that was a crucial, something I've learned in a lot of these aerospace flights is amazing things can happen in a tenth of a second. And you can spend months of computer time trying to simulate and understand what might happen in a tenth of a second, and that's something that happens here. The same thing that you'll see, they're also concerned about what happens as this crew module eventually comes down and hits the water. The dynamics of this vehicle hitting the water are quite complex too, and the main forces occur in a fraction of a second, but again, we spend a lot of time trying to understand what happens in that short time. Had anyone heard of this particular flight? It was about 2 years ago. It was a successful flight, and it was managed by an organization here at NASA called the NASA Engineering Safety Center, or NESC. I believe the NESC was set up shortly after one of the shuttle accidents to ensure that we have a good safety culture and robust engineering culture in our projects. Here's a close-up again of that separation sequence. And in the lower left, you see a CAD model or a computer model of actually where our cameras are. Each one of those cones down here, the green and the cyan, yellow and red, represent the wide field of view that each of our cameras had. The cameras were actually sitting on the crew module looking out in 4 different directions. Each camera is looking out at that shroud canopy that covers the crew module. And the three black and white images are it's an actual sequence of images from one of these cameras as that canopy is released, it raises up, and we can see it moving. So the idea here is that if we know something about where all these white dots are located on the object, then we can determine how fast is it moving and exactly what is its orientation as it moves along. For this particular test, we had our cameras were running at 200 frames per second, and these were wide-angle cameras. They actually use a fisheye lens, and you can see there's a bit of distortion. You might be able to tell in those images. At the bottom of the image, there's a lot of curvature from these wide field of view cameras. You'll see quite a bit of distortion like that. So our next challenge was, can we understand what that distortion is? Can we calibrate the cameras and determine how much motion is going on in the scene? Fisheye lenses also have been around a long time. They're used a lot by photographers to get special effects. They're used originally by meteorologists to look at the whole sky. With one picture, if you use a fisheye lens to take a picture of the sky, you can capture all the clouds. It's used by scientists looking at the canopy of trees in the forest. And you can use reverse projection. You can actually have a lamp and use a fisheye lens to project an image all across the room. It's used in an IMAX spherical dome, for example. It's used in planetariums. And even that little peephole in the door of the hotel room has a little fisheye lens in it, so you can see a whole hemisphere around you. So again, we used a hemispherical lens on these cameras to essentially capture the whole sky. Not only were the fisheye lenses used to look at these targets, but they were also used to record what was going on with the parachutes. Remember, there's quite a few parachutes in this process, so our cameras were watching all the motion going on with the deployment and motion of those parachutes. Let's see. So this is a schematic showing something about how our cameras were oriented inside this vehicle. Our cameras are represented in blue. We had 3 or 4 of these cameras. They have what we call non-overlapping views. Each view was independent. They didn't have any overlap of targets, whereas conventional photogrammetry traditionally requires an overlapping view, much like the way your eyes work and your mind works. You actually see 3 dimensions because your 2 eyes have an overlapping view, a slightly different view of the object in front of you. So you can use your 2 eyes to deduce something about 3 dimensions of the world in front of you. If you don't have this overlap, as we have in blue here, there is no overlap between our cameras, so we had to use something other than the binocular stereotype vision. Essentially we had to develop our own algorithm to characterize the motion of this object if your cameras don't overlap. Here's a little bit more about conventional versus a fisheye lens. If you look at the bottom corners, we took a photograph of a checkerboard. With a typical lens, there's very little distortion, and the checkerboard has pretty straight lines on it, and you can characterize any distortions in the lens pretty easily. On the lower right, you can see a photograph of a similar checkerboard with a fisheye lens. There's going to be quite a bit of distortion of the checkers, and I've also drawn there a 3-dimensional representation of how the light rays are collected and projected into the camera lens center. On the left-hand side, with the traditional lens, it's a very linear relationship. They call it a collinearity between an object, its point on the image plane, and the center of a camera. It's a pretty simple relationship that's been used for 100 years to understand how cameras work. It's quite a bit more complex if you use a fisheye camera. This 3D curvature down here represents the dispersion of light rays that a fisheye lens can collect and bring in. If it has to take a picture of the whole sky and fit that onto one image plane, there's going to be quite a bit of distortion in the process. But it turns out we did our research, and there were some others that have looked at using a fisheye lens for photogrammetry for actual measurements, and we found a way to calibrate this kind of lens to understand and quantify this distortion. It turns out you can use a fourth degree polynomial to represent how this light is scattered across the image plane. I think let me go to one of my backup slides. Here's a tool we found that was a result of some research in Switzerland at the Swiss Federal Institute of Technology, where they actually, the way to calibrate your camera is to take a bunch of photographs of a checkerboard with that camera, and then you analyze each image individually and say, you pick out the corners of every checker. There are some tools in there to help you in that process. And in the end, if you analyze every one of these images, you can build an internal model representing how light is bent and distorted and brought into the camera. And it turns out we can understand that down to less than one pixel on the image plane. So this was just one lesson about there's research out there. You need to see what's out there. It may not even be in your state or your country. It may be in another country. But with the World Wide Web, it's pretty easy to find out what people have been doing research on. It became quite helpful. So this type of tool is free and available to anyone who wants to use it. And there's another tool available from Caltech. It's also free. We used a Caltech camera calibration tool for a more typical type lens, the type that doesn't have the distortion. You may have heard your week or two here about the MATLAB tool. Some of you may have used MATLAB or a similar tool. We again use MATLAB. MATLAB's required to use these pieces of software, but it's a very powerful general purpose tool, and I do think students and teachers can get a discount on using MATLAB. You probably have they learned about MATLAB or heard of other tools that are similar that might be of use? Okay. That are going to use it. Oh, good. All right. Yeah, I might point folks to the Caltech camera calibration toolbox is very useful if you want to start experimenting with photogrammetry. And they're on the web. So the Caltech toolbox will be useful for standard lenses on the left, but for a fisheye lens on the right, you'll need something else like that toolbox from Switzerland. So once we've calibrated our cameras, that allows us to take any point in our image. Points of interest are these the red pluses in the center of every target. Remember, these are those important, what we call fiducial marks on the object that we're going to track. So we have software that will look for those targets, find the center of them, and with a calibrated camera, you can take any 2D point in an image and understand what ray of light that came from. So it's a mapping from 2 dimensions into 3 dimensions that we use all the time in camera photogrammetry. So keep this in mind. We have a camera. We're taking 2D points and getting 3D lines from them. We use that. This is what our algorithm looks like. I won't go into a lot of detail, but the idea here is that we have a couple of cameras down here that are observing targets on their image planes, and those targets are actually coming from a large 3D object that's out there in the real world. And that 3D object is moving, it's translating and rotating over time. And we want to be able to understand how far did that object rotate, how far did it translate. And it just takes a little bit of math. It's called linear algebra. Has anyone used matrix math? Multiply one matrix times another. That's exactly what we would do here. I'm not going to show you all the matrices, but in general, these equations up here you would expand into matrix form. Who said thank you? Okay. No, I won't put you through that. But the idea here is, and this comes up in computer graphics a lot. If this is a rigid body that's rotating and translating to a new position, you can represent that in matrix algebra as a rotation matrix and a translation matrix. So that's our first equation up there. The new targets locations are equal to the original targets times a rotation and a translation. Yep.
So in order to I do teach some matrix work, and
All right.
in order to engage them, I have heard, and so I hope I'm correct. I'm sure you'll be able to tell me. I've heard that with computer graphics, the kind you see on the television screen, that is a matrix-based graphic system, and or it used to be. So
Usually is.
The NFL symbol,
Yeah.
kind of twirl and then go away. All of that is done by computer-generated matrix graphics. Is that correct? Or is it done a different way now?
I think if the object appears solid and it's not flexing or undulating or something like water, if it's a solid object, then it probably is. Its motion, its rotation, its translation is being performed internally using matrix math. Computer graphics has been the real engine behind it has been matrix math to make it possible. To this day, we still use it. I've used it quite a bit the last 2 years to represent all the objects and mathematics you see here. So it's certainly. I had no idea when I was in college how useful the linear algebra would be. It's a little strange at first because you go beyond simple arithmetic and you look at whole blocks and whole matrices of numbers, and just multiplying. The first thing to learn is matrix multiplication is not as straightforward as you would think. Addition and subtraction is pretty easy, but multiplication is a big leap forward that you have to master. And but once you've done that, there's a lot of power behind it. Just about every computer model that we run out here, whether it's a fluid dynamics model or an aerospace motion model or a climate model, it's almost always some matrix mathematics behind it. And MATLAB excels at doing the matrix multiplication. You don't have to do all that yourself. In fact, we rely on MATLAB heavily in order to solve these equations for us. We do the work in setting up the matrices and setting up the math, but then we just sort of hand it over to MATLAB and say, here, you solve it for us. So there's something called a closed form solution that you would like, but it's not always available for equations. So something like MATLAB will iterate on your equations and converge toward a solution, at least a solution that is as close as possible to what you want, because there is no perfect answer as there would be with simple equations. So again, that first equation is a matrix equation that's pretty common in computer graphics and photogrammetry. The second one is a little different. It just represents the fact that these targets out in 3D space lie along a line of sight from your camera through the image and out into the real world. So in a sense, there's this object out there, and there's only one place that it can be positioned and oriented so that it matches what you see in your cameras. Your cameras see dots. That's what we're looking for. These dots are these targets. And there's only one orientation that fits what the cameras see, and that's the orientation what we're looking for. So it turns out that these two equations you can set equal to each other and hand it over to MATLAB and say, here, solve it for us. And it does a good job. It's called a nonlinear system because it has some sines and cosines and tangents in it. And we found that it works for one camera or 2 or 10 or 100. The mathematics are scalable. And we found that you can have 2 cameras overlapping, looking about the same place, or they can be looking in different directions at the object, and it still works. So it's a very flexible algorithm. And we've used it for the wide-angle lenses and the more conventional lenses. It works in either case. And it seems to be very robust. We've thrown all kinds of complex problems at it, and it comes up with a good answer. And as you'll see shortly, even when your object is splashing into the water and you got all these water droplets around, it still works. We still have a good solution. So the linear algebra works if you just plug and chug through it, and it's amazing what it can do once you have programmed it correctly. Of course, there was a lot of debugging in the process. You all probably been through the computer code debugging process. It can be interesting, but it's rewarding when you finally get it to work. So What kind of programming languages do you know? Is there one that you use for the linear?
Octave and MATLAB as a result.
Right.
But, I used to teach a long
Yeah.
time ago, basic, of course, Fortran,
Right.
77. We've heard a lot about that here.
Yep, still used out here, isn't it?
Pascal. And then once C came around, I
Mhm.
kind of trickled off and didn't do it anymore.
Oh,
C++, Java, C#.
yep. Those are very popular. I wish Pascal had remained popular because it was a good language to learn. It had good syntax and very understandable, very strong typing, as they call it. You couldn't be lazy with Pascal, whereas you can be lazy and dangerous with C or C++. So, but C++ and Java are very capable and useful languages. Are used all over the place now. Is Fortran still used here? I believe it is.
Here.
They were saying.
Yeah, yeah,
The engineers like it.
yeah.
You know, people who use C.
I know that C or C++ is among the fastest out there. Was there a question or comment back there?
What do you think we do about that? We have been data simulations in Excel spreadsheets, corresponding dynamics.
Right. They're probably better at Excel than I am. I'm still learning Excel. The more you look into it, the more it can do, isn't that true? All right. So here's some results from our photogrammetry analysis of that max launch abort system. Of course, we know that the two objects are going to separate, so the main signal we're going to see is how much is that separation. And that's what that's what this curve is up here, if I can find the mouse. There it is. This blue curve here represents the main displacement in that vertical direction between the two objects. Notice it's a smooth curve. It's not a noisy curve. Our algorithm would be doing a poor job if there were a lot of noise in that curve. But we got a pretty smooth result showing that over time these two objects displace fairly cleanly. You'll see a couple other lines. There's a red and a green line represents motion in the other two axes. It didn't move that far in either one of those axes, but mostly as we expected in the vertical direction. Have you heard of the expression degrees of freedom? Here's 6 degrees of freedom. We have the 3 translation directions and the 3 orientation directions. So the plot on the bottom shows our 3 angles. One of our angles is quite steady and the other 2 vary. In fact, you can see in that photograph there's going to be 2 major angles. There's going to be that twist and there's going to be a rotation towards you. So that's what you'll see. There's 2 other curves there representing those 2 major angular degrees of freedom. So the photogrammetry algorithm successfully extracted both the 3 dimensions of translation and the 3 orientations. That's another area of matrix math that can get pretty hairy is rotation matrices and the order of rotation. One of the first things you learn in linear algebra is the order of matrix multiplication matters. Unlike in algebra, it doesn't really matter what 2 times 3 times 4 is the same as 4 times 3 times 2, but not in matrix math. So that's something we always had to keep in mind when doing 3-dimensional or 6 degrees of freedom. Now, we also kept track of something we call the residual error, because as these 2 objects get further and further apart, the image gets a bit more fuzzy, the object is further from us, we can't see those targets as well. So we do expect to have a little bit more error as to where the 2 objects are located from each other. So we were able to keep track of that error. I think it turned out to be, even when the object is 16 feet away, our error was less than 1/4 inch. So we were still able to quantify what was going on. And this wasn't the only way to measure what was going on between these 2 objects. They have accelerometers on board that could measure what are the g-forces as these 2 objects separate. And you may have had someone talk about inertial systems and dynamic simulations. It turns out if you integrate accelerations twice, you can get these displacements. So we had an engineer do that as well, and he got results that closely matched what we have here. So that's something we try to do with experiments out here, is have two independent devices measuring something similar, and if the two agree, then that improves your confidence in the answer. Is there any questions about that? There's this experiment was performed in 2009, and remember, the vehicle launched, reached its height, and came back down with the parachutes and hit the water. And turns out there's a lot of interest now, not only in this separation of the two vehicles, but what are the dynamics once it hits the water? What are the G-forces experienced? If we had astronauts aboard that crew module, what would they feel as they hit the water? And of course, that's how the Apollo astronauts returned from the moon, and Gemini and Mercury as well. They did splash landings in the ocean. It's been quite some time since we've analyzed and studied water landings, so there's renewed interest at NASA in the dynamics of this environment. Let's see. We want to ensure that the G-forces aren't too extreme that the astronauts would get injured. So you can imagine, just from your own experience in the swimming pool, if you hit the water with a belly flop, you're going to feel a lot of force. However, if you dive into the water, you're going to easily glide right into the water without much problem. So it turns out then with a crew module, you don't want to land it straight down. You're going to have an incredible amount of deceleration and G-forces in a belly flop. So you're more likely to land at an angle like this to help alleviate the G-forces. It turns out you can glide right into the water quite a bit easier with fewer forces at an angle than if you were to plop straight down. Does that make sense? Just like a diver versus a belly flop. Yes?
I understand what you're saying.
Mm-hmm.
It's almost like the dynamics of the capsule. I'm thinking, to try and explain it to my kids, but
Right.
The difference in acceleration sort of through your body versus head to toe.
Right.
Changes makes it. So how are the astronauts positioned in this capsule that's going down?
I think usually their feet would be at the corner that, or the first part that hits the water is where their feet would be.
And are they sitting down or laying down?
They'd be sitting down, I think.
Sitting down.
Of course, this one's, in this test, there's no one in it, but
Someone must be thinking about it.
yeah, certainly. That's why we have instruments all over this thing to understand what's going on. Now, the way we did this test was we said, okay, if we did in fact have parachutes, even if we're coming from space, we're slowing down, we have parachutes, we hit the water. We only hit the water at about 25 feet per second. Well, that's about the same as if you just dropped a vehicle, if you drop this object from a crane from about 10 feet, you'll hit the same velocity. So that's exactly what we did. If you use simple equations of motion, that's how you determine, well, just drop it from 10 feet. You'll hit the same velocity as if you were on parachutes. So that's exactly what we did up at Aberdeen Proving Grounds in Maryland. Does anyone know where that is? It's just north of Baltimore. They had a large pond there and a crane that allowed us to bring our crew module up there and drop it from the crane. And we've dropped this object now about 60 times to collect data. We did about 20, let's see, we did it about 20 times in 2010 and 40 times in this year in 2011. Just repeatedly to understand the dynamics of this entry into the water. You would think in this, here it is 2011, we should have analysis tools that could easily predict all the dynamics. Where's the water going? What are the forces? What is the deformation of the crew module as it hits the water? But it turns out to this day that's still an extremely difficult problem. And they've gotten pretty good at predicting what might happen in the first tenth of a second as this hits the water. But after that, it's difficult to predict exactly what will happen. So that's why we still had to perform these tests with a real object in real water to help essentially calibrate our codes or validate what our software, our simulations are doing. For example, they like to know what is the maximum depth that this crew module goes under the water. Our software simulations have difficulty predicting that. That's why we have to do this test to understand ourselves, to see how deep it does go under the water. There were two particular angles that we were interested in. One's about 20 degrees and the other's at 30 degrees. As you might imagine, the lower the pitch angle, as you get closer to zero, you're going to hit the water with more force and you're not going to go as deep. So the idea is the higher that angle is, the smoother that it'll be, and maybe the deeper you'll go into the water. And you'll see some plots for that. This time we no longer need those fisheye cameras. We can use typical 35 millimeter cameras. They have less distortion anyway. So here, these three images are actually from our three cameras, high-speed cameras, looking at this same scene. Once again, you'll see those dots, our targets on the object that our cameras will track, all those white dots. And this gave us another chance to try our algorithm on an even faster camera. This is 1,000 frames per second, 5 times the rate at that launch test we did. And it gave us a chance to just show that our algorithm was continuing to be robust and accurate and flexible. Some other folks here at Langley that worked with me on this were Dan Yuknovic, Tom Jones, Benny Lunsford, and Paul Bagley. Let's see. So here's our photogrammetry software actually chewing away on this image. And what you'll see it doing is, you might be able to see these green and blue plus marks. Those are targets that it's found in the field of view. It's going to be tracking those targets as the basis of its algorithm. I think you might also see that red circle around the object. That's what we call a region of interest. I tell the software to look only within that circle and ignore anything outside the circle. Sometimes we got a lot of sun glare off the water. Sometimes the software might think, oh, that must be a bright target, but it's not. So I would tell it to not even look outside the circle in that area. So once the software picks out these targets from 2 or 3 or 4 cameras, it uses that matrix equation you saw on the previous slide to help calculate where the 6 degrees of freedom are occurring. In other words, we want to know, as this enters the water, how much is it rotating and how much is it translating into the water. And that's what this software will tell us. Another class that was useful in undergrad school was statistics. A lot of times I had to report to the engineers what is the accuracy and the confidence of this data, what is the mean and the standard deviation and so forth. What kind of errors are we expecting from photogrammetry so that they can understand what kind of confidence level to have in the results. I'll show you a little bit about the accuracy of our measurements. The software we're using here, there is MATLAB. We're still using MATLAB in the background to do the intense math. It's being supplemented by image processing software from, it's a software called LabVIEW. It's used quite a bit here at Langley. It's used at some colleges too. It's particularly used to as software to control robots or other devices or interface to instruments or measurement devices. It's pretty good at low-level I/O, and it allows you to visualize signals from those I/O devices or record signals from your robot or tell the robot to do certain things. So it's good at signal processing and image processing. Has anyone heard of LabVIEW or seen that at the schools? Really? Yeah. Is that a robotics project? Okay. I thought LabVIEW was used quite a bit for robotics. Let's see. Here's a plot where the horizontal axis is time, and the vertical axis, at least for the red plot, is distance traveled vertically over time. So as we know, if an object is free falling and you plot that over time, the shape of the curve should be a parabola, at least very close to a parabola, unless you have a lot of air resistance. And it turns out that during the free fall, the photogrammetry did in fact see motion very close to a parabola. In fact, it was, You know how much a millimeter is? It's like that, a quarter of a millimeter, you can barely see. That's how close we were to an actual parabola. And that's one way to measure the accuracy of the photogrammetry. If we were saying that our object was varying from a perfect parabola and there was a lot of noise behind that, then we wouldn't have a very good algorithm. But the fact that we were able to actually see parabolic free fall as it drops from the crane, that gives us an indication that we have a good solution. So the origin there, where all these lines come together, that's where we hit the water. So when you hit the water, you would expect it to now start decelerating. And that's why the red curve starts to curve in the other direction. It represents that we're no longer free falling. We're starting, even though we are entering the water, we're starting to decelerate. And I'll have a video to show you here in a second where not only do you move vertically, but eventually you start, once you hit the water, you start moving forward, essentially moving down the channel. Maybe I'll go ahead and show that video now to give you an idea of what we saw. I believe it's running in the background here. View. Okay, so once again, this is a result of a high-speed video running at 1,000 frames per second, looking at the crew module right when it starts hitting the water. We've supplemented it with some computer-generated imagery. That mesh or that grid you see on there is a result of our photogrammetry. We've actually projected the 3D model back onto the video so we can see a little bit better what's going on. See, at that point, there's a lot of water there obscuring the crew module. That's why we projected this grid back on there using computer-generated imagery so that we could better visualize what's going on. And you'll see it come out of the water. You see it goes fairly deep into the water, quite a few feet, at least that back end. So if you were inside, you'd be feeling deceleration and a lot of this pitch motion going on. But there's what do you call the force that eventually pushes it out of the water? The buoyancy force takes over very quickly. Even though you have a lot of mass and a good amount of velocity entering the water, the buoyancy force starts taking over, and we call this the Shamu maneuver. It just sort of propels it out of the water.
Did the original capsules 20, 30 years ago, did they land flat or did they land at an angle?
I'm pretty sure they landed at an angle. Do you what's that?
Did they video it? Was anybody close enough? Did they know where the ones?
Well, the Apollo program did do some tests similar to this, and there is some video or some photographs.
But the actual one we didn't.
I believe there is some PR video, of course, of some of the splashdowns. I've seen that before. Yeah.
It seems to me, though, when I've seen it, they actually come in at the opposite angle. They're, it's like their backside is hitting first, but I could be wrong. So it's almost flat. It seems like it's flat. They didn't know it was the one, but that's what my recollection is from seeing some of that archival video.
That's a good point. I haven't seen it in a while, but we actually had some Apollo former astronauts or staff as consultants on this project, and they actually compared some of our data with data from 30 years ago, and they were very pleased with the results we got here. They were very pleased with the photogrammetry. They didn't have such sophisticated abilities with photogrammetry back then as we do now. Let's see. So here's a look at the angles. I mentioned that there were two primary angles that we tested, one at 30 degrees inclination and one at 21 degrees. So if we look at it turns out if we're at the higher angle of 30 degrees, the red line represents our translation into the water. So we actually go a bit deeper into the water at that higher angle. As you go shallower, closer to a belly flop, you're not going to go as deep. So the green lines represent how far we went in when we were at a shallower angle. And again, these are derived from the photogrammetry. Now you might see on the right side of the curves, they do get a little noisier. And just look at the lower right of the green curve and the right curve. The reason we see more noise there is there's a lot of water droplets in the air. We don't have as many targets visible to us. So the photogrammetry it's more challenging to come up with a good 6 degree of freedom solution in that case. But still, it comes up with a good answer. And there's a close-up of that capability to take a CAD model and map it back onto the 2D video that helped us visualize a lot better the dynamics of what was going on. Turns out there's been some, they can do smaller tests on a vehicle only this big around, again looking at how the heat shield of a crew module would enter the water. So they actually have a pool out here, just a couple blocks from here, a small swimming pool, where they can drop small specimens, and once again we'll use photogrammetry to analyze what's going on. You'll see some of those targets applied to the test specimens so we can track what's going on. And we have a brand new facility out here at Langley, a full-scale Olympic-sized swimming pool basically, where we can do our own testing with full-scale crew modules, just like we did at Aberdeen. They just started testing a few weeks ago. And that may have been in the news, actually. Let's see. We're doing continuing research with this algorithm. After finishing up the MLAS launch test and these Orion water tests, we're starting to look at applying it to the new large swimming pool facility out here. We also believe it has applications in space with the stage separation. If you have two objects, again, separating in space, if there's targets out there, our algorithm can look for those targets and tell you something about the relative separation of your two objects in space. We're very interested in using the full sky camera capability of these fisheye lenses, using them in the atmosphere or in space. And if you think about using the stars in the night sky rather than targets, you should be able to that'll tell you something about the orientation of your space vehicle. Star tracking has been used quite a bit over the last 40 years, but we believe there's even new research to be done in tracking the stars in a full sky application. So my colleague Sam Miller is doing PhD research in that area. And we've actually submitted a patent for some of the technology that you've seen in this presentation. So hopefully the U.S. Patent Office won't take but 2 years or instead of 3 to process that application. They've got quite a bit of backlog. And I think I have a couple photographs from our experience at Aberdeen. Back in 2010, the D.C. and Baltimore area experienced what they called Snowmageddon, I think. They had when we got to Aberdeen, there were about 6 feet of snow on the ground, but we continued with the test. You can see a lot of snow behind me. I'm up on a wall looking down on the facility. There's the crane we used to drop the crew vehicle, and you can see hanging back there is the crew module itself on the lifting crane. It was about 25 degrees that day and windy and snowy, but we managed to perform the tests. And here's a few more photographs of that test environment. And there, you can see our team down there to give you a sense of scale, just how large this crew module is. It's quite a bit larger than the Apollo crew module. You can see the Apollo crew module in museums. NASA's planning our next crew vehicle to be much larger. It could hold more astronauts. So you can get a sense of the scale of the experiment. I think that's about all I had, and I'd like to entertain any questions you might have. Thank you.
Can we get the video?
I will, let me make sure, there's another video that I have cleared. I haven't quite cleared this one for distribution. But I'll,
Like the overlay.
the overlay? Okay. All right, I'll make sure.
If you get that one cleared, we'd love to have it.
Okay. I'll try to do that. All right, we did hit about 1 hour, so very good. All right.
Is there any application that you can see, high school level, that they can either afford the software, the hardware, or they, I don't know, anything?
I think there's application in robotics experiments. If the robot is trying,
And maybe as a lead off, there's lots of schools that have like little mini TV studios,
Mhm.
and green rooms.
right? I think there's a lot of interest in the motion tracking of people. It's used a lot in Hollywood and in entertainment, in gaming. I would think a lot of students have an interest in that. So you could set up an experiment in the lab where students put on these targets, and the cameras can watch those targets, and the computer could process that imagery and reproduce the motion that was observed in the room. You could also have a robot looking at a targeted object and learn how to grasp it and interact with it as well. And just do a Wikipedia search on photogrammetry to get some other ideas of how it can be used. There's quite a few toolkits out there that allow you to do some of this processing. Maybe, and we'll try to get our software in a shape where we can release it someday as well. Make it easier to use. There's a lot of you may have seen on that one image. I don't know if it showed all the buttons. This only shows a part of all the knobs and buttons on our software. We're going to try to make it easier to use. I know the JPL uses a lot of photogrammetry, Jet Propulsion Lab, California, on a Martian rover to examine where the rocks are, what's the size of the rocks, are we clear enough, can we fit through those two boulders, for example. Photogrammetry will tell you exactly what's going on there. They certainly outfit the rovers with several cameras to understand the three-dimensional field of view that it's experiencing. All right, anything else? Well, thank you all very much.
Thank you.
All right.